this works. All right, so this is Math 150, Section 2, Lecture 18, depending on how you count, because now we had the issue with the review from the midterm. So what I want to do today is just do one problem of switching orders of integration, and then really talk a lot about polar coordinates and change of variables. I will motivate this by giving you one of the most important integrals in the history of humanity, and how painful it is. And the goal will be to show you how painful it is so that you will not complain when we do the painful change of variable formula. And you will see that all pain is relative. Okay? So in terms of techniques, in one variable calculus, we don't have that many techniques for integration. We have U substitution, we have trig substitution, we have integration by parts. I asked people in the first section, what's the least favorite of all the integration techniques? And somebody said integration by parts, and that is one of the few wrong answers you can have. You have to like integration by parts, right? Anybody know what the worst technique is from Calc 1? The most hated? Partial fractions, right? It turns out partial fractions are very useful, but I think when you are a high school student, freshman in college, the partial fractions is the least favorite. We don't have that many techniques in multivariable calculus. This is both good and bad. From a homework testing perspective, it's good. There's not that many things to try. From a, I want to use this material to solve things that matter in life perspective, it's bad. You don't have that many options. Big ones we have is switching orders of integration and changing variables. The changing variables is often to exploit asymmetry. So people have asked me, how do you tell which one to do? It's basically a decision tree. Step 1, can you do the double integral as given? If yes, do so. If not, try one of the various things. First thing is maybe switching the orders. Maybe that will help. Let me try that. If it doesn't help, put it off to the side and then say, well, maybe I could change variables. And then if that doesn't work, well, maybe switching orders wasn't so bad, or maybe trying to do it directly wasn't so bad. And you can go back and you can revisit. So here is a following problem. This is a cookbook problem. I'm integrating y goes from 0 to 2. I'm integrating x goes from y over 2 to 1 of y e to the x cubed dx dy. So we first integrate with respect to x, and then we integrate with respect to y. So if I'm integrating with respect to x, I view y as a constant, and I need to find a function f of x such that its derivative is e to the x cubed. So fast forward 7 or 8 minutes, we now have given up and discussed that all of the things we tried to find a function whose derivative was e to the x cubed have failed. Okay? So in the interest of time, if you've seen the movie Click, we're just going to fast forward those 7 minutes. All right? We're going to try something else. If that something else doesn't work, we can utter some profanities and go back and then try to do this again and find an antiderivative. But for now, we had no luck finding the antiderivative. Let's try to do it another way. Well, step 1 is always to look at what does the region of integration look like. This is not a candidate for polar coordinates or spherical coordinates. I don't see any radial symmetries or anything like that. So let's draw the region. Well, the first thing we notice is all of the items are always non-negative. Y goes from 0 to 2. So here is 0, and here's 2. All right, now, if I give you a value of y, the question then is, what value of x do we have? What's the range for x? Well, x goes from y over 2 to 1. So what's nice about this is no matter what value of y you start with, you always end at x equals 1. So we start at some point and we go until we hit the x equals 1. Where do we start? Well, let's take a couple of values. If I take y equals 0, then we start at x equals 0, so we start down here. If I take y equals 2, we start at 1. If I take y equals 1, we start at a half. And as you take more and more points, you begin to see that this isn't just a straight line. And the integration looks like this. Fix a value of y, and then x runs from this line to that line. And the line is x equals y halves. So you give me a value of y, and I know the corresponding value of x. Okay? Let's switch the order of integration. Does the region physically change when I switch the order of integration? No, it's the same region. I'm going to just redraw it. I have a lot of good chalk today. It's the same region, and I want to keep the drawing uncluttered. So rather than going horizontally, let's try going vertically. So now I fix the value of x, and I have to figure out what value of y. So what's the lower value of y always going to be? 0. So this will be the same as the integral x goes from 0 to 1. And now y goes from 0. And what's the upper bound? How high does y get?
2.
I'm sorry? Almost 2, not quite 2.
2x.
2x. So we have the line x equals y halves. So given a value of y, here's what x is. I now need to convert this to y as a function of x. So if x equals y over 2, then y equals 2x. It's the same straight line, but I'm now changing my perspective. I'm now viewing it as x is the input and y is the output. So y goes all the way up to 2x, and now I have the function y e to the x cubed dy dx. I now need to find a function whose antiderivative is y. Just y squared over 2. So the y integration is very nice. At this point, we don't know if the resulting x integration will be nice, but we're at least able to make some progress. In the first one, we were just screwed. We had no hope of finding an antiderivative e to the x cubed. Y, we can find an antiderivative. So we get e x cubed, we get y squared over 2 evaluated at 0 and 2x dx. Okay. Well, when I evaluate it at 2x, I get 4x squared over 2, which is just 2x squared. When I evaluate it at 0, I get 0. So we get e to the x cubed 2x squared dx. Does this look promising? Yes. We have an e to the x cubed. We'd love to have what down here? Yes. We'd love to have 3x squared. We have 2x squared. If you are upset that we don't have a 3x squared and this is not good enough for you, multivariable calculus is not for you. This is as close as you have any reasonable chance of getting. We can fix this easily. I want a 3, multiply by 3 over 3. And I can pull out 3. This is the same as just 2/3 integral x goes from 0 to 1, e to the x cubed 3x squared dx. And now this is set up beautifully for u substitution. So there's 2 ways we can do the u substitution. What's one way we could do u substitution here? Yes.
16.
One is to have u as x cubed. There's another way we could do u substitution.
E to the x cubed?
Yeah, we could make u e to the x cubed, and then du would just be e to the x cubed 3x squared dx. So this would just become du. So you actually have 2 choices here. I'm going to do u equals x cubed. So that means du is 3x squared dx. X goes from 0 to 1, so u also goes from 0 to 1. And again, I really think it's worthwhile to just be pedantic, write down all the stuff, make sure you're going to get the bounds of integration right. If x goes from 0 to 1, what does u go from? And now I'm left with the 2/3, the integral u goes from 0 to 1, e to the u du. All right, so that's just 2/3 e to the u at 0 and 1. We get 2/3 e minus 1. And so we now have the answer to the problem. What should we do with our answer? What should we do whenever we get an answer? Check it. Well, it's often hard to check it, but we need to find another way to do this integration, which I do not know. So if we can't check it, what could we at least do? It's not quite as good as checking, but...
Wait, what are you asking?
So I can't check the answer. I wanted, what else can I do to, yes?
To figure out if it makes sense.
Yeah, figure out, does it make sense? One of my students from Brown was in finance many, many years ago, and something didn't look right, and he did a quick check and got that the answer was absurd. Turns out there was a minus sign in the wrong spot. And this was right before the company did a significant investment. You want to make sure your minus signs are in the correct spot. You want to have some sense, is this answer reasonable? What kind of test can we do? All right, well, let's look at what we're integrating. We're integrating the function y e to the x cubed in this triangle. what's the largest this function can be? How large could y e to the x cubed be? Yes? 2e, right? Largest y can be is at 2, largest x can be is 1. So the maximum value is 2e. What's the area of the triangle? So what's the area of our triangle? So base is 1, height is 2, it's just going to be 1. So the integral has to be less than equal to 2e times 1. We have 2/3 e minus 1. It's definitely less. And it's less by a reasonable amount. I don't expect this to be close to 2e all the time. And so if you wanted to do better estimates, you could split the triangle up into smaller triangles and have lower and upper bounds. But just as a ballpark, we got something positive, we got something less than 2e. Seems reasonable. So as much as possible, this is what you want to do. Okay? Yes?
Why is the triangle, why does that not give us the exact answer?
Because the function is not always equal to 2e. If the function was always 2e, then it would be exact. So what we're saying is the largest it can be is at this point at 2e. The smallest is going to be down here at 0. So we know the true value is somewhere between 0 and 2e. If we divided the triangle, you maybe divide it and look at everything up to y equals 1 and everything from y equals 1 onward, we could do a better lower bound and a better upper bound. But I don't care about this problem that much. And given that I have all of you following my work here, and I've also done this problem in section 1 earlier today, I'm quite confident that the answer is 2/3 e minus 1. All right. So what I want to do now is I want to do one of the most important integrals in all of mathematics. And it will be a terrific motivation for why we need to learn the change of variable formula. In its full generality, the change of variable formula is a nightmare. I took a wonderful integrated year-long course in multivariable calculus, linear algebra, point set topology, and vector analysis as a freshman. I did not tell you guys this yet, correct? All right. Sometimes hard to remember what I told section 1 and section 2. You did a little bit of linear algebra, then you stopped, and you did multivariable calculus with the benefit of having linear algebra. Later today, we're going to need to take determinants. What class would be wonderful to have in your back right now? Linear algebra. We don't have linear algebra. So this was a wonderful class in that sense, in that you developed both subjects almost simultaneously. The problem is if you don't finish the full year, you know half of multivariable calculus, half of linear algebra, you don't have the prereqs for any further class, and you're basically in a screwed state. But it is very useful to see how you can use the linear algebra and then actually have the linear algebra available. So what I want to do is I want to give you the proof of the change of variable formula in certain cases. It's been 20 plus years, my memory's a little foggy. I'm pretty sure when the semester ended in the spring, the professor was proving the change of variable formula in as great generality as possible, and we used every letter of the English alphabet, most of the Greek, and I think some Hebrew. The proof just kept getting more and more general in terms of the spaces and mappings we can consider. You can go that route. We are not going to go that route. We will concentrate on why is it true, what are the key ideas, and then the big three. Polar, cylindrical, spherical. Okay? Here is the problem. Imagine you have a sphere, and we'll say the sphere has a uniform density, and because it's symmetric, we might as well assume our mass is right above the sphere. And I want to calculate what is the force. So you're building rocket ships, stuff like this matters. You're putting satellites in orbit, stuff like this matters. If you don't care about stuff like that, please hand me your cell phone. Right? We can't get away without our satellites in orbit now. So how do we calculate the force? Well, Newton's law of universal gravity, we will assume today Newton is right and Einstein is wrong, is every object in the universe pulls at every other object with a force that's inversely proportional to the square of the distance. For galactic scales, Newton is fine. There are some things where we need things very precise, and we do have to take into account special and general relativity. Not today, right? So for each point inside the sphere, we will calculate what is the force. Now what's nice is if we have a point over here that's going to be pulling us like this, there's a corresponding point over here that's pulling us in the other direction. So the only net pull is in what direction? Down. So all we will have to do is calculate what is the pull downward. What letter do you normally use for density? I'm sorry?
V.
V? That was rho.
Rho.
You normally use rho, right? Unfortunately, we can't use rho for density today. Why can't we use rho for density? Yeah, we have spherical coordinates that are going to be lurking in the background. I don't want to use D for density because that could be confused for differentiation. I'm running out of letters. I will use B for Back to the Future, for George McFly. All right, so we will say the density is B. So I have a small little block on the sphere, say dx, dy, dz. Its mass would be B times dx, dy, dz. And I want to calculate what is the force. So here is some point x, y, z. And let's assume the sphere has radius 1. So I'm going to just try to draw things a little bit. Here's my point x, y, z. I will assume the center of the sphere is the origin. I will assume I am r units up north. So this is the point 0, 0, r. Here's some angle alpha. Here's the point 0, 0, 0. So if I want to calculate the distance is just going to be x, y, z minus 0, 0, r. So the force is going to be g m1, and it'll be b dx, dy, dz. That'll be my small infinitesimal mass at x, y, z. I have to divide by the square of the distance. All right? So this vector is going to be x, y, z minus r. So its length would be x squared plus y squared plus z minus r squared. Now I should take the square root for the length, but then I need to immediately square it for the force, because the force is 1 over the distance squared. When I say force, that's the force in the direction between these points. I want the force that's coming down, so I need to multiply this by the cosine of alpha. How would I find the cosine of alpha? I need to figure out how much to depress the contribution of the force. Do you know anything from chapter 11 that can give you the cosine of an angle? Law of cosines would give it to you if you have the lengths. Dot product. So we actually have this length, we have this length, and we have that length. So we could actually do it with the law of cosines. We could also do it with dot product. Either one is fine. So if we do the law of cosines, I think it's a little bit nicer to do it with the dot product, but either way is fine. So this is the vector x, y, z minus r, and then this would be the vector 0, 0, negative r. So the dot product, v1 will be x, y, z minus r. v2 will be 0, 0, negative r. And then v1 dotted with v2 is going to be the length of v1, the length of v2, and then the cosine of the angle between them. Well, the length of v1, that's basically just the square root of our denominator here. That's not bad. The length of v2, that's just r. Great, that's the distance we are. That's looking good. So we feed this in as cosine of alpha is going to just be v1 dotted with v2 divided by r, and then we have to divide by the length of this. So we then have the square root of this. So we have this times its square root, so we get this whole thing to the 3/2 power. Now we have to integrate. What's the region of integration? Well, just make things better. So we're integrating over the entire sphere. So we're not just on the boundary. So x goes from -1 to 1. Given a value of x, y goes from negative square root of 1 minus x squared to the square root of 1 minus x squared. And then z goes from negative square root of 1 minus x squared minus y squared to the square root of 1 minus x squared minus y squared. So if you ever feel that I am making you do things that are unreasonable, this is what you're not doing. Write down the integration explicitly and try to do it. You're welcome to use Mathematica or any software you want to try to evaluate this integral. This is the integral we need to do. And the miraculous answer is that when the dust settles, it is as if all the mass were concentrated at the center. Which is wonderful because it means these problems are much easier to do. You don't have to worry about integrating over the whole thing. Okay, so as an exercise, write down explicitly what you have to do here and try to actually evaluate it. I was thinking hard over the last day to see if there was a simpler way to do this than using full spherical coordinates. And I was saying, what if I give you a circle, and we can then show that if I have a circular ring, it's as if all the mass was at the center. Then all I have to do is just spin the circle, and I'll get the sphere, and I'd be done. And so I spent a lot of time trying to prove this before I finally realized the reason I can't prove this is because it's false. If I have just a circular ring, it is not the same as if all the mass was at the center. Here's a good way to see this. Imagine I have my mass here. Here's 0, here's 1, here's 2, here's -1. And I put masses here and here. Is the force of these two masses on my object the same as twice the mass over here? Well, let's calculate. The force on this one on here, it's 1 unit away, so it would be 1 over 1 squared. This one is 3 units away, so it would be 1 over 3 squared. So you get 1 plus 1/9, or 10/9. If I put all the mass at the center, my mass is now doubled. The distance now is 2, so it's 1 over 2 squared, so I get 1/2. So if I just had a rod, and I had an object above the rod, it is not the same as if all the mass of the rod is at the center. If you had a circled ring, it's not the same as if all the mass was at the center. But spin the circle and have a sphere, yes, it is the same as if all the mass was at the center. So what's wonderful about this is that for the problems that we care about in three-dimensional space, it all works out. So this is an integral that must be done. This is not one of the cookbook examples like the one I gave you at the start of class that just doesn't matter. This one we need. Or without this, we lose our satellites in orbit. Okay. So this will be hopefully the motivation for why we're going to learn polar coordinates, spherical coordinates. Yes?
Why do we need to put the 2/3 exponent over the denominator?
So we initially had the denominator to the first power. Oh, I have to drop the r. Sorry. No. So the r stays. Sorry. The r stays. Because we had the length of v1, length of v2 in the denominator. The length of v1 is x squared plus y squared plus z minus r squared square root. So we then had another factor of x squared plus y squared plus z minus r squared to the 1/2 power. We had it to the first power, so 1 plus 1/2 is 3/2. So you can see this is just going to be a nightmare integral to do. And we really need to learn these new techniques. Okay. So we're going to start with polar coordinates. And we'll basically only get to polar coordinates today. But we'll do 3 different proofs of why polar coordinates change the way they do. And these proofs, the third one at least, will generalize to other settings. So polar coordinates. So we have x is r cosine theta. We have y is r sine theta. If I have a circle in Cartesian space, this is what a circle looks like. Maybe x squared plus y squared less than or equal to big R squared. And if we go into polar space, What does a circle look like in polar space? It looks like a rectangle. So here is our radius r, here is 2 pi. And so the circle looks far better in polar coordinates than it does in Cartesian coordinates. But we need to figure out what the exchange rate is. How do we measure the infinitesimal area here? How should we measure the infinitesimal area here? Let's take a circle of radius 1. What's the area of a circle of radius 1? Nope. Pi. And of the circle of radius r? Pi r squared. So this has area pi r squared. What's the area of this rectangle? Yes, 2 pi r. So we can't just say, dx dy transforms to dr d theta. This is going to clearly be wrong. The area here is not the same as the area there. So we have to figure out what the conversion factor is. The other thing is, units are enough to tell us that this is wrong. If x and y are in meters, area is meters squared, dx dy, great, meters squared. But dr d theta, that only has units of meters. Theta is just an angular measurement. And this is why I think that the correct conversion factor is r dr d theta. And this has units of meters squared. But we should not view it as r dr d theta, although we will always write it that way. We should view it as dr times r d theta. And the reason is r d theta now is a length. And so when I write it this way, I can see it's a length times a length. That's going to be an area. The reason we use radians is if I use radians, if I have an angular measurement like this, and I want to know how long is the arc that corresponds to it, the length of the arc is just r times theta. That's not the case if we use degrees. We have this conversion factor of 360 and 2 pi. But when we use radians, the length of that arc is just r theta. Okay, so what I want to do now is I want to do the first justification for why it's r dr d theta. So we're going to start off, actually, I think I can even see the circle from 9 o'clock. So here is a circle. Here's my angle theta. Here's my radius r. I'm going to increase my radius by a little bit, by delta r. And I'm going to increase my angle a little bit by delta theta. I'm not going to draw this to scale. Delta r and delta theta are supposed to be very small, tending to 0. And I want to find out what is the area of that patch. So the first thing is, let's find the area of the whole ring. So the area of the whole ring is big circle area minus little circle area. It's probably not really good to say big circle and little circle because they're almost exactly the same size. We'll do outer circle, inner circle. What's the area of the outer circle? Yes?
R plus delta r squared.
So pi times r plus delta r squared. And then the inner circle is just pi r squared. Okay. Now, we need to figure out what fraction of the annular ring do we have. So what fraction of the annular ring do we have? Yes? Delta theta over 2 pi. So if delta theta is equal to 2 pi, we have the whole circle. So this gives us the percent of the ring we're getting. So if delta theta is pi halves, that's a quarter of the circle. And pi halves over 2 pi would be a quarter. Now in practice, delta theta should not be as large as pi halves. It should be extremely small. All right, so now if we expand, the first term will be pi r squared will cancel with a pi r squared. And so when the dust settles, we get 2 pi r delta r plus pi delta r squared times delta theta over 2 pi, or the 2 pi cancels with that 2 pi, and we get r delta theta plus 1/2 delta r squared delta theta. And now we can say, well, what happens in the limit as delta r and delta theta go to 0? So what do you think the r delta theta is going to look like in the limit as we get smaller and smaller and smaller?
RDRD theta.
Yeah, that's our RDRD theta. And this would really, it's going to be 0. And the reason is we have an extra delta r. We have 3 infinitesimals, but we only get to do 2 integrals. So imagine you have a stick, and you break it up into small little pieces, delta x, and you sum them all, you get back the length of the stick. If I had delta x squared, when I sum all the lengths, when I sum all the delta x's, I get back the length, but I have an extra delta x just floating around. And so it would be multiplied by another delta x, and it would be 0. We have too many delta r's here. We'd have an extra infinitesimal floating around, and this will not contribute in the limit. And so this tells us that if we use polar coordinates, we should be getting r delta theta or r drd theta. So this is how we have to convert. This is what the dx dy goes to. So dx dy goes to r drd theta. Okay. Any questions on this? Okay, so this is the first of the ways of doing things. I'm trying to remember. There was a second way that I did in section 1, and I'm blanking on what was that second way. I'm not remembering now. I thought there was another way. It doesn't generalize as well, so I'm not that worried that I'm forgetting what that way is now. We'll spend a little bit more time on the third way, which does generalize better. If there was a second way, I will check the video later and just tell you, you watch these in a few minutes. So we start off with x, y, and I'm going to do it in more general notation, and we will specialize at the end to polar. So we have x and y. Actually, we'll do it the other way. We have u and v, and we want to convert back and forth to x and y. So maybe u and v is r and theta, and we want to go from polar to Cartesian or Cartesian to polar. So for polar, we have x equals r cosine theta, y equals r sine theta, or conversely, we have r is the square root of x squared plus y squared, and theta is arctangent of y over x. Let's say I have some map. So T takes u and v as inputs and gives me my x and y as outputs. So it's going to give me an x as a function of u and v and y as a function of u and v. There are 2 ways to do things. I did it the wrong way in the first section. This is the advantage of being in the second section. The notation will now work out nicely for polar coordinates later. I can go the other way around. I don't like to discriminate. I have s of xy. That will give me u as a function of x and y, and v as a function of x and y. So we're assuming we're in a situation where you give me one set of variables and I can give you the other. Okay? And the question is, we want to figure out how do we relate dx dy to du dv. So we need to find the exchange rate. We now know that the exchange rate in polar is a factor of r. Dx dy equals r drd theta. That's the exchange rate. In general, it's going to be some complicated function of s or t. Right, so we're clear on the setup. Right. So today we're beginning to see a lot of the advantages of the material from chapter 11. So we're going to see a lot of that right now. So let's start off at some point. Some point t of u naught v naught. And we'll call that point x naught y naught. So you give me a u and a v, and then t tells me where I am. And it's going to give me a pair of points. And I want to look at what happens if I change u and v by just a little bit. Well, if I change u and v by just a little bit, what's my new x, what's my new y? Do you want to change both u and v, or do you want to change just one of them first and see what happens? Should we change both of them, or should we change just one of them first? Yeah, let's just change just one of them. Do you want to change u first or v first? U. Does it matter? No, but this is just typically the way we do it. We've got two things. Let's change just the first one. Let's look at the point t of u naught plus delta u and v naught. So we want to see how things change. So this is going to be the point x of u naught plus delta u v naught. Comma, y of u naught plus delta u v naught. I have my pair. I've just changed the value of u. I'm keeping the second one the same. So I need to figure out how my function x changes. X is a function of u and v, and I'm just changing the first component. If delta u was 0, I would just get back x naught. So my answer, it should look like x naught plus a little bit. Where have we seen this before? Not the definition. The tangent line, right? If you want, forget about v naught. Imagine we're just in one variable. We have x of u naught plus delta u. We approximate it using the tangent line. So this would be x naught, and then it would be dx du times delta u, right? And now what about the second component? It would be y naught plus dy du delta u. And that would be the change. And so if I want to look at this vector, what would be that vector? So the vector is going to be this pair minus that pair. The x naught cancels, the y naught cancels. So the vector is just going to be dx du delta u, dy du delta u. Right? Now let's look at the next one. So now we have the point t at u naught, v naught plus delta v. So we play the exact same game as before. So this is going to be x of u naught, v naught plus delta v, and then y of u naught, v naught plus delta v. And now we use the tangent line again, and we see how has it changed. Well, it's going to be, if I was at the point u naught, v naught, that would just give me back my x naught. I'm keeping the first component fixed. I'm only changing the second component. So where am I approximately? Where do I start? Plus instantaneous speed times elapsed time. So it'll be x naught plus, now I'll have partial x, partial v times delta v, and then y naught plus partial y, partial v delta v. And then this vector is going to be, I subtract from the point x naught, y naught, I'll get partial x, partial v delta v, partial y, partial v delta v. We could also change not just the first component, not just the second component, but both, and go to the point t of u naught plus delta u, v naught plus delta v. That point would be here. T of u naught plus delta u, v naught plus delta v. Anybody want to guess what kind of shape this is? parallelogram. So it's not necessarily going to be a rectangle, but it's approximately a parallelogram. Is the tangent line perfect? No. T of u naught plus delta u v naught is not going to be just going along this line as I increase delta u. It'll curve ever so slightly. But if delta u is very, very small, it's approximately that straight line. Same thing for here. So what's really going on is as long as delta u and delta v are very, very small, the delta u, delta v is going to go back and forth with our delta x and delta y, but it's going to be a parallelogram for one and a rectangle for the other. So it's going to be a rectangle in UV space, delta u, delta v. And in the xy space, it's going to be a little bit different. It's going to be a parallelogram. Well, we don't have how to calculate the area of a parallelogram. So this is where we use our determinants. So the area of the parallelogram. So the first vector is partial x, partial u, delta u, partial y, partial u, delta u. The next one is partial x, partial v, delta v, partial y, partial v, delta v. We take its determinant, and we get dx du times dy dv. We have a delta u, delta v here. We have a delta u, delta v for the other one. I'm going to just pull that out. Minus dy du dx dv delta u, delta v. And so this tells us how a change, dx dy is going to look in the UV space. Where should we test this on? What change of variables? What's the one case we've really covered so far? We've done polar. So we do x is r cosine theta, y is r sine theta. We have to calculate, so basically u will be our r and v will be our theta. So we have dx dr times dy d theta minus dy dr dx d theta times delta r delta theta. What's the derivative of x with respect to r? So what would be the derivative of x with respect to r? It would be cosine of theta. So I'm just trying to make sure it stays in focus. Come on, move back. All right, so the first one will just be cosine theta. What's the derivative of y with respect to theta? So the derivative of y with respect to theta. It'll just be r cosine theta. And minus dy dr, which will be sine theta. And then we have dx d theta, which will be r negative sine theta. So the negatives reinforce. And then we'll have delta r delta theta. And so we would get r cosine squared plus r sine squared. Oh, what's cosine squared plus sine squared? 1. So we get r delta theta. And so that gives us back the polar coordinates. And this is the way that we'll generalize. This is the way that we'll solve a variety of problems. Is a small rectangle is transformed to a parallelogram. It now works for the polar change. The spherical change is going to be a little bit harder. We have to use a parallel pipette. We have to now use the determinant of a 3x3 matrix. This is where you really want to know linear algebra. All right. So what I want to do is, we've got 5 minutes left. I want to do an application. So in the interest of time, I'll skip the first example we did in section 1, and I'll just go straight to the one that really, really matters. So the one you could have done is, integral x goes from -1 to 1, integral y goes from negative square root of 1 minus x squared to the square root of 1 minus x squared e to the negative x squared plus y squared dx dy. So as an exercise, use polar coordinates and do this one. If you try to integrate this directly, it's not going to work. So rather than looking at this one, I want to look at an integral that's very similar to this, but it's an integral that actually matters. And so the integral is the following. I want to look at I is the integral from minus infinity to infinity of 1 over the square root of 2 pi e to the negative x squared over 2 dx. So this is an integral we can't do using Calc 1 techniques. It is a one-dimensional integral. Now the question is, why do we care about this integral? The normal distribution with mean mu and standard deviation sigma has density 1 over square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared. How many of you have heard of the normal distribution, the bell curve, the Gaussian? When you have this many names, you're important. Okay? A lot of things in the world are normally distributed. And if I integrate this from, say, 3 to 5, this will tell you what's the probability you take on a value between 3 and 5. To be a probability distribution, you need two things. You need to be non-negative, good, and you need to integrate to 1. So we need to show that when you integrate this, you get 1. This is the special case when the mean is 0 and the standard deviation is 1. It turns out if you can do that case, you can do all the other cases. So we want to evaluate this integral. We can't do this, you really can't do this using Calc 1 techniques. But it can be solved amazingly cleanly using multivariable calculus. So sometimes it's better to take one step backwards to then take 2 steps forward. We're going to convert from a one-dimensional integral to a two-dimensional integral so we can use the techniques of multivariable calculus. All right? So we're going to square the integral. So it's either I am or I squared is the integral x goes from minus infinity to infinity, integral 1 over square root of 2 pi e to the negative x squared over 2 dx. And now I'm going to write the integral again, because I'm doing I times I, but I'm going to use a different letter this time. I'm going to use the letter y. And I'll get the integral y goes from minus infinity to infinity, 1 over square root of 2 pi e to the minus y squared over 2 dy. All right, so this is the following double integral. X goes from minus infinity to infinity. Integral y goes from minus infinity to infinity. The 1 over 2 pi square roots reinforced. I can pull out a 1 over 2 pi. You might be wondering, why is there a 2 pi coming into this Gaussian integral? And we have e to the negative x squared plus y squared dx dy. So this is very similar to the integral I did in section 1. I said, let's just do the one that really matters. We need an antiderivative for e to the negative x squared or e to the negative y squared. We don't have that. Changing the order of integration is not going to help us because it's symmetric at x and y. If you switch the order of integration, you get back to what you started. So we have no choice but to try changing variables. Since it only depends on x squared plus y squared, the integrand only depends on x squared plus y squared, let's try polar coordinates. So we would have, this is the same as 1 over 2 pi, the integral theta goes from 0 to 2 pi, integral r goes from 0 to infinity, e to the negative, oh, that should be over 2, e to the negative r squared over 2, r dr d theta. And I mentioned earlier in the day that if you were upset that we had a 2x squared instead of a 3x squared, you were being overly picky. Everything works out beautifully here. I have an e to the negative r squared over 2. I want an rdr. I've got an rdr. So I have a double integral to do. The theta integral is really easy. There's no theta dependence. So because there's no theta dependence, what do we get when we do the theta integral? So what will the theta integral give us? I'm sorry? I couldn't hear what you said. It'll give us 2 pi. So when we integrate with respect to theta, we get 1 over 2 pi, integral theta goes from 0 to 2 pi d theta, integral r goes from 0 to infinity, e to the negative r squared over 2 r dr. This is going to just give us a 2 theta, which cancels, 2 pi, which cancels with the 2 pi here. And we're left with the integral r goes from 0 to infinity, e to the negative r squared r dr. This is negative e to the negative r squared at 0 and infinity. E to the negative infinity squared, that's really 0. All right? So we get 0 minus e to the negative 0 squared. Or what's e to the 0? 1. And so when the dust settles, we get 1. So this proves that the area under the curve is 1, that it is a probability distribution. This gives you some sense of where the pi comes from in the Gaussian. So how many of you have seen the Gaussian before? How many of you have wondered why the hell is there a pi going on in the Gaussian? It's coming from this change of variables. It's coming from a polarness that's lurking. Yes?
So why is it not negative 1?
Oh, sorry. Because I dropped a minus sign when I was writing, because I have to subtract the. All right. So this is a good place to stop. Have a good rest of the day.